Hello everyone, this is Rashid Kibria from Fixed Research, University of Florida. In this demonstration, I will analyze the flattened gate level netlist of Z80 CPU core using FSMx-Ultra. The Z80 CPU core was very complex, as you have already seen in the RTL analysis of the core using RTL FSMx. I have already synthesized the core using design compiler. One thing I need to mention, I have also modified the state encoding to binary perfectly because the default FSM state encoding there, it was not that good. Most probably they wanted to use the one-hot encoding approach, but I see the state encoding was very bad. So I have basically changed that to a pure binary state encoding system. That means all the 46 states, they are enumerated from 0 to 45. I have now let's start analyzing the flattened gate level netlist of it using FSMx-Ultra. So you can find FSMx-Ultra inside our gate category. If you select it, it will open up a graphical user interface. First, you have to add the technology library which was used during synthesis in .lib and .p format. For the demonstrations, I am actually using Z80 90 nanometer technology from Synopsys. It is an academic usage technology library, so you can basically use it for academic and research purposes. However, FSMx-Ultra is able to handle any advanced technology libraries as well. I have tested my tool on 14 nanometer technology from ARM, that is the GF 14 nanometer or GF12 LP plus, most probably that library. Yeah, so FSMx-Ultra is able to handle any sort of technology library, and also you can use any commercial synthesizer for the synthesis of your RTL design. Cadence genus, it can be also used. There are no issues. I have also analyzed the netlist generated from Cadence genus as well. It also works without any problem. So I will basically load the technology library now in two different formats. You can find it inside a library folder. This one is the .lib file, and then the technology library in .v format. Now I will read the flattened gate level netlist. You can find it inside inputs, and Z80.v, it is the flattened gate level netlist generated by Cadence genus. Design compiler from Synopsys. So I add that and hit open, it will add it. There were only one control FSM. So the FSM extraction report, which was generated from RTL FSMx here, I am inputting that. Now I will click on the extract control FSMs button. It will take just a few minutes to compile to generate the graph representation of the entire netlist and perform structural analysis on that to identify the state register, extract the FSM report. So you see the FSM extraction process finished in only 2 seconds. Now the Synopsys Tetramax ran, and gate level FSM extractor tool is working to extract the state transition graph in a graphical format. So there are total 6-bit encoding. So 64 files were generated using Tetramax, and my gate level STG extractor tool analyzed that to show you the state transition graph. Yeah, you see the process is already completed. Now you can see the extracted reports here. So Z80 report, that is the folder. Here we'll see 3 things: netlist directory, statistics, and ISTG report. In netlist directory, you will find the extracted control FSM minimum extraction region and the pure combinational state transition logic. So FSM_1.v, it is the FSM minimum extraction region of the control FSM for Z80 core. And it basically consists of the state register and the pure combinational state transition logic. So here you see it is a pretty massive netlist. It is a lots of gates here. That is why I have already told that this control FSM is very complex. Not only in RTL, after implementation, it is still so much complex. Yeah, you see this file is very big, lots of inputs here. So if you look here at the inputs port, we have a huge number of inputs, primary inputs basically. As the number of primary inputs is very high, you cannot use exhaustive gate level simulation to extract the state transition graph, which was basically being performed with the FSMx tool. That is why FSMx is not that much scalable, but FSMx-Ultra is able to scale because it uses ATPG-based analysis to extract the state transition graph. If you try to extract the gate level STG using FSMx, it will obviously fail for this region because you see we have a huge number of primary inputs here. And just if you look here at the inputs, apart from clock and reset, the others are basically our inputs. So just look here, it is a huge number of inputs, input pins here in the primary input pin of the FSM minimum extraction region. These input pins are also obviously present in the pure combinational state transition logic. That is the thing overall. So yeah, the STG was extracted perfectly. Now we can view the state transition graph in graphical format. You can find it inside STG_report folder. Here .png file, only one FSM there. So I will basically select here and click open. It will take now just a few seconds to show us the state transition graph, because as I have already mentioned, the STG is so much complex. So just look here at the STG. It is so much complex. It's lots of states and a huge number of state transition. And if I try to zoom in a bit in a certain part of the FSM, so just to focus on here. So yeah, you see, we have a huge number of state transitions going on. Yeah, it is because of the complexity of the state transition logic there. And we see 1, 2, 3, 4, 5, 6, or so 6-bit state encoding, because the state register has a width of 6 bits. Now I want to show you another report that was also inside this statistics folder. This is basically a CSV file also generated by FSMx-Ultra. If I open it, so you will get a report here. There are some significance of it. The first field is the name of the FSM state register. Second one is this field is the size of the state register. Next, FSM probability metric, the number of extracted gates or number of gates present in the FSM minimum extraction region. So we see here 230 gates are present, including the 6 straight flip-flops there. So apart from the, if you subtract 6 from 230, we will get 224. That means we will have 224 other non-sequential cells, which basically forms the state transition logic. That is why FSM, the pure combinational state transition logic for this control FSM is very complex. It is a large number of gates and large number of primary inputs, and that is why FSMx actually failed, but FSMx-Ultra succeeded. This really emphasizes that FSMx-Ultra is way better than FSMx. That was a quick demonstration of FSMx-Ultra on a complex CPU core Z80. Thanks for hearing.